Hi there, this is Professor Shannon Gracey from Maricosta College. Today we'll be covering section 5.5 from the Larson and Edwards Calculus text. Today we're covering bases other than E for both logarithmic and exponential expressions and functions. So this is something that doesn't come up a whole heck of a lot in, calculus 2 and 3, but you need to know how to apply the formulas and check all this stuff out. All right, so let's get going on this and warm it on up. So we'll start off with practicing on logs. We're going to evaluate the expression without using a calculator. So remember, the way we read this is the power, the first one, here I'm on A, the power to which I raise 12 to get 144 is, whoops, sorry. Oh, wrong color here. Let's see, and all right, we're all set now. Okay. So this will be equal to, good, 2, because 12 squared is 2. All right, so next up, we've got the power to which we raise 4 to get 1/16. So what do you think? Good. That's going to be -2. Because 4 to the -2 is 1/16. And the power to which I raise 1/5 to get 25. What do you think? Good. This again will be -2, right? Because it would flip that 5 to the numerator and you'd get the result of 25. Okay, so let's take a look at sketching, this graph without using our graphing calculator. So if we make ourselves a little grid here, this is x and this is our function at x, and let's see, and we're going to have, actually, let's do this. Let this be -3 and 8. All right, ready to go? So here what we have is, we've got your input x and your output f at x, and then you've got your ordered pair that comes out. Okay, so here we go. We if we put in, I don't know, start at x is -2, this would be what? F at -2 is equal to 2 to the -2 is going to be 1/4. Good. So our ordered pair will be -2, 1/4. And then -1, F at -1 is, good, 1/2. So we'll have the ordered pair -1, 1/2. And then 0, F at 0 is 1. So we'll have an ordered pair at 0, 1. And then let's see, we can do, let's do 1 and 3. So F at 1 will be 2 to the 1, which is 2. And F at 3 will be 2 cubed, which is 8. Good so far? Awesome, awesome. All right, so now let's go ahead and plot these ordered pairs. So this one's going to be real close to here. This will be a little more up. But then we'll be at 0, 1, and then at 1, 2, and 3, 8 is about there. All right, so again, nice smooth, pretty exponential curve, and this one here is, they're all going to look pretty similar when you've got your base greater than 1. It just depends on how rapidly they will grow. Okay, so here we go. Definition. Exponential function to base a. So if you've got your base a as a positive real number that's not equal to 1, and x is any real number, then the exponential function to the base a is denoted by a to the x and is defined by a to the x is equal to e raised to the ln times x. So you're probably wondering where that all came from. If you just sort of take a look over here, if you have your a to the x going on, right? Now, if you evaluate e at the natural log function, you basically have an equivalent expression, right? Because the natural log and e are inverses of each other. And this, in turn, using properties of logs, is going to give us e raised to the x times natural log at a. And then we just commuted those terms, those factors, actually. So e to the natural log at a times x. So now, here we go. So if a is 1, y is 1 to the x, which is equal to 1, which is a constant function. So definition of logarithmic function to base a. This utilizes the change of base. You're used to seeing it more like log base a at x is equal to natural log at x divided by natural log of our base a, right? And all they did is rewrite it with 1 over natural log at a as a multiplier. Okay, so here we go. Properties of logs. So sorry, my numbering is off here. 3 and 4, and then 2, 3. Okay. All right, so log base a at 1. So the power to which I raise a to get 1 is, beautiful, 0. The power to which I raise a to get a is 1. Now, the log of a product is the product of the logs. So just like in our natural log section, you just have to be careful. You're writing this as log base ax plus log base a y. All right, and then what happens with that power rule there? You've got the power comes down as a multiplier and to the log. And then, there's really one that's kind of missing here. Let's go ahead and add it in. What about log base a of this quotient x over y? That ends up being log base a of the numerator minus log base a of the denominator. Okay, so again, I'm going real quick because we went over these in more depth in the last section. or the last couple sections. So properties of inverse functions, y is a to the x, if and only if, that's what the IFF stands for. So basically you write log, that's the first step, right? Your base is a, right? And then a logarithm is an exponent, which was x, right? And what's left is the y, okay? And again, if you the base of a and a logarithm base a, those are inverses of each other, right? This one I meant to have an x inside there, so if you can change that, that'd be great. And so here you're just going to get x because you're evaluating a at logarithm base a, so you get what's inside the log. Similarly here, you're evaluating log base a at a to the x, so that x is the result. Okay, so derivatives for bases other than e. So first is the case where you do not have a function of x, right? So what will happen is, just like before, you rewrite your exponential just like for the logarithm of e to the x. But what we need to do is we need to multiply this by the natural log of our base. So it's usually written as natural log at a times a to the x. So here, what do you think is going to happen? Beautiful. We'll have the natural log at a. We are going to have du dx, or u prime, because you're using the chain rule, right, on the power. And then what's happening? Beautiful. You have your exponential exactly as it was. Okay? Alrighty. Now, derivatives for logarithms. Instead of multiplying by natural log of your base, you divide. So what will happen is you'll have your 1 over natural log of your base a, right? And then times 1 over x. Okay? And if you have a function of x going on in that log, what will happen is you will have 1 over natural log at a times du dx, or u prime, and then times 1 over u. Cool so far? All right. I guess I can be more consistent and write these with parentheses. Okay, so now here we go. Y is equal to 2 to the negative. All right, let's start out by differentiating both sides with respect to x. And on the left side, we'll get dy dx, or y prime, whatever you prefer. And here, remember, we want to rewrite the exponential exactly as it is. Right? And then we need to, differentiate the power with respect to x. And the power was negative x. And then don't forget, we got to multiply by, beautiful, natural log at 2. So we'll have y prime is equal to, y prime is equal to, perfect, negative from the derivative with respect to x of negative x, so that's negative 1, and then natural log at 2 times 2 to the negative x, and a product, right? And part of that product has an exponential factor. And within that exponential factor, we've got a function of x. So there'll be a little bit going on here. So, differentiating both sides with respect to x, we will have dy dx, or actually we've got f prime of x is equal to, so remember we'll have, I'll just write it out the first couple times, we'll have d dx of x, right? And that's going to be multiplied to the exponential unchanged. And then we'll add to that x times the derivative of that exponential, which was 3 raised to the 8 minus x squared, and then we'll have times natural log at, beautiful, 3. So this will give us f prime at x is 3 raised to the 8 minus x squared plus x times natural log at 3 times 3 raised to the 8 minus x squared, and this derivative has a result of negative 2x. Okay, so cleaning it up a bit, we will have f prime at x, at x is equal to, I'll factor out the 3 raised to the 8 minus x squared, and I will end up with 1 minus 2x times natural log at 3, and we are all done. How'd you do? Awesome. Okay, so what do we have for this one? Overall, we have a perfect, a quotient, right? So here, what do we need to do? We'll differentiate both sides with respect to what? Perfect, t. And then on the left, we'll have f prime at t is equal to. So I'll just use the quotient rule. So remember, we have the derivative with respect to t of our numerator, which is 4 raised to the 2t, and then that's multiplied to the denominator, and then we'll subtract from that the numerator times the derivative with respect to t of our denominator, and that's all over the denominator squared. Cool so far? All right, so now we will have f prime at t equals. So differentiating the exponential, you will have what? Perfect. We'll rewrite the exponential exactly as it is. That's the most common mistake people make. And then the derivative of the power with respect to t. So we'll be differentiating that to t with respect to t. And then one more thing, what am I going to have? Perfect. Times natural log at 2. And then don't forget, you're still multiplying this by t. Minus 4 raised to the 2t. And what's the derivative with respect to t of t? Good. That'll just be 1 times 1. And that's all over t squared. Good so far? Great. F prime at t will be The derivative with respect to t of 2t is 2. Perfect. So we'll end up with 2 times natural log at 2, and then multiply that by 4 raised to the 2t. And actually, the nicest way to write this would be 2t times natural log at 2, because we have that t being multiplied, minus 4 raised to the 2t all over t squared. And finally, we can factor out the 4 raised to the 2t, and we'll be left with 2t times natural log at 2 minus 1 all over t squared. And we are done with that guy. All right? Good so far? Great. Hang in there. All right, so what do you think we might want to do for part D? Well, we've got a logarithm with a different base than e, so we're going to have to deal with that. But we have a property of logs we can use, right? Because we have a quantity that's inside the log that's raised to that third power. So why don't we rewrite g of t as 3 times log base 2 at t squared plus 7. Good so far? Great. So differentiating both sides with respect to t, we will have g prime at t equals, the 3 is going to go along for the ride, right? And this derivative is going to be what? Okay, so remember, we need to do 1 over what is inside of the log. That's one of our jobs. Times d dt of what's inside of the log, which is t squared plus 7. And what's the other thing we need to do? Multiply that by 1 over natural log of our base, which is 2. So these are all being multiplied here. Good so far? All right, so g prime at t, don't hurry on these, okay, because that is something that could mess you up. All right, so what are we going to have? We're going to have the 3. The derivative with respect to t of t squared plus 7 is what? 2t. Good. And then that'll be over natural log at 2 times t squared plus 7. So cleaning it up a little, we have g prime at t is 6t over, I guess I'll just write it as t squared plus 7 times natural log at 2. Good so far? Awesome. All right, so next up, what might we want to do with this guy? Perfect. Use properties of logs again to change it from the log of a quotient to the difference of two logs. So y is equivalent to log, and remember, this is the common log, so the common log has a base of what? Perfect, 10, right? So log of something, call it m, is equivalent to log base 10 m. So here we go, differentiating both sides with respect to x. We will have y prime is equal to, so we can do these derivatives individually, right? So we're going to have d dx of log base 10 at x squared minus 1 minus d dx of log base 10 at x. So continuing, y prime will be, so what do we do first? Good. 1 over what's inside, which was x squared minus 1, and then times d dx of what's inside the log. Am I missing anything? Good. We need times 1 over natural log at 10. Am I done with the problem? No, that's just the first term, right? So next up we'll have minus, this one's going to be a little simpler because there's no function of x in the log. So this will just be minus 1 over x, and then times 1 over natural log at 10. Good so far? Great. Okay, so here we go. Continuing, we will have y prime is equal to the derivative with respect to x of x squared minus 1 is 2x, and then that'll be over x squared minus 1 times natural log at 10 minus 1 over x times natural log at 10. So now let's get a common denominator. So I'm going to need to multiply the first one by what? X over x, right? And the second one I'll need to multiply by x squared minus 1 over x squared minus 1. Now do you see we've got a common denominator? So y prime will be 2x squared minus x squared plus 1, distributing that minus through, all over x times x squared minus 1 times natural log at 10. Okay, so far? Alrighty, so y prime will be x squared plus 1 over x times x squared minus 1 times natural log at 10. And we're all done. How you doing? You hanging in there? Great. I know you can do it. Okay, so antiderivatives of exponential functions that have a base of a. There's a couple ways you can do this. You can use the fact that a to the x is equivalent, that a to the x, right, is equivalent to this, right? And if that's the case, what happens is your u sub, right, would be equal to natural log at a. So your du dx is equal to, oops, sorry, that would be natural log at times x. So then du dx would end up being what? Good, natural log at a. So if you isolate your dx, you'd end up getting 1. So dx, isolating dx, you would have du over natural log at a. So if we put it into, we back substitute here, this would give us what? E to the u, good, And then we'd have our du over natural log at a, which would give us 1 over natural log at a times the integral of e to the u du. And then you would go ahead and that one is just going to be what? E to the u over natural log at a, and our u was e raised to that natural log at a times x. So you end up getting a to the x divided by natural log at a and then plus c. Okay? All right, so I'm okay either way. You just got to learn how to do these. So we're going to find the indefinite integrals and then evaluate any definite integrals. So we've got 3 to the x, okay? Typically, students would much rather me just use that formula, so I'm going to go ahead and do it that way. But just remember, you can always go and do it the other way. So this one is going to be what? What's my a in this case? So if you wanted to sort of make a list, my a would be, good, 3, right? This antiderivative ends up being 1 over natural log at 3 times 3 to the x plus c. So we can write it just as 3 to the x over natural log at 3 plus c. We're good to go. All right? Okay, what do we have going on this next time? Right, we've got to do a little work here, don't we? So here, if we were to let u equal to what's in that power, du dx would be what? Good, 3x squared. And then if you isolate dx, you're going to get du divided by 3x squared. So let's see if that worked out for us. So coming back over here, we'd have the antiderivative of x squared times 8 to the u, and then in for dx we would have du over 3x squared. Good so far? So this is what went where. Our dx is all of this. Our u was 1 plus x cubed. And then fortunately, the x squareds divide out, and we're going to end up with 1/3 times the integral of 8 to the u du. And that's going to give us what? Good. 1 over 3 times natural log at 8, okay, so far, times 8 to the u plus c. And then cleaning it up and back substituting, we're going to have 8 raised to the 1 plus x cubed all over 3 times natural log at 8 plus c. Okay, so far? Great. All right, so what about this guy? Here, just a small u substitution. U is negative x. Du dx is negative 1, so dx equals negative du. So we will have the integral of 5 to the u times negative du, which is going to give us negative integral 5 to the u du, which is negative 1 over natural log at 5 times 5 to the u plus c, which will give us negative 5 to the negative x over natural log at 5 plus c. Okay? All right, so next up we have a definite integral, right? And we've got 2 of these terms here, right? So this one, we're not going to have any u substitution, which is nice, because we just have these two different bases raised to the x. So let's check it out. We'll have, good, 6 to the x over natural log at 6 minus 2 to the x over natural log at 2. That's going to be evaluated from x equal to 1 to x equal to e. Cool so far? Great. So we will have 6 to the e over natural log at 6 minus 2 to the e over natural log at 2 for our upper limit of integration, minus 6 to the 1 over natural log at 6 minus 2 to the 1 over natural log at 2. So 6 to the e minus 6 all over natural log at 6. I'm just combining these, and then we'll end up with factoring a minus, right? This guy will be 2 to the e in the first parens. And then let's see, the other one's supposed to end up as a positive, so we're going to have minus 2 over natural log at 2. If you want to pretty it up, you can. I'll take one more step. This would have been okay. We'll end up, if you get a common denominator, with natural log at 2 times 6 to the e minus 6, and then minus natural log at 6 times 2 to the e minus 2 all over natural log at 6 times natural log at 2. All right. So now let's look at an application. We're going to find the area of the region bounded by the graph of y equals 3 raised to the cosine at x times sine at x. Y is 0, x is 0, and x is pi. So let's check it out. Remember that our area, as long as you've got positive outputs, is going to be equivalent to the definite integral. So here you've got an exponential function that always has positive outputs, so we're good to go. So here we go. Our area will be equal to the integral from, so our x bounds are from 0 to pi, and we have 3 raised to the cosine at x, and then times sine at x with respect to x. Okay, so far? All right, so we're going to want to do a u substitution of u is cosine at x, du dx is negative sine at x. So we will have dx is equal to du over negative sine at x. Now, I don't know why this came up. So now what we'll have to do is change those limits of integration. So we had u as cosine at x, so u at 0 is going to be cosine at 0, which is great, 1, and u at pi is equal to cosine at pi, which equals negative 1. So putting it all together, we will have our area is equal to the integral from 1 to negative 1 of 3 to the u times sine at x, and in for dx we have du divided by negative sine at x. So dx is this stuff here, and then our u was cosine at x, and we got these limits of integration. Our bottom one was that positive one from over here, and then the top limit was -1. So remember that little trick so we don't end up with a bunch of weird negatives? You can write this as the integral, negative the integral, and then switch the limits from -1 to 1. And let's see what happened here. Do you see that the sign at x's divide out, which is good? And there's I'll just do an extra step. So then we'll have 3 to the u times negative du. So that first negative is from flipping those limits of integration. And so now we'll end up with the area is equal to the integral from -1 to 1. That negative makes it positive, the negative inside. And we'll just have 3 to the u du. So we'll end up with 3 to the u over natural log at 3 evaluated from u equals -1 to u equals 1. So our area will be, I can bring out the 1 over natural log at 3, and then we'll have 3 to the 1 minus 3 to the -1. So our area is 1 over natural log at 3 times 3 minus 1/3. And what's that going to be? 9/3 minus 1/3 is 8/3. So the area will be 8/3 over natural log at 3, and that's equal to 8 over 3 times natural log at 3 square units. All right? And if you wanted to be, really fancy, you could write this as how? Perfect. 8 over natural log of 3 cubed, or natural log at 27. And that would be in square units. Okay? All right. So, next up. After T years, the value of a car purchased for $25,000 can be modeled as the value at time T is 25,000 times quantity 3/4 raised to the T. Right? So, we're going to use our graphing calculator, okay, to graph the function and determine the value of the car 2 years after it was purchased. Not sure. Okay, gotcha. Okay, so we would just be doing 25,000 times and that's going to be raised to the we'll just do x in this case. ddx of just copy this. So ddx of all this. Okay, so there is our, oh nice, so we've got our derivative, and we've got our derivatives in blue. think I almost have it where I want it. Okay. There we go. So our derivative's in blue and our original function is in red, right? So here, if we take a look, let's see what else this program will do. So at 1, to 1. At 1, we are at negative 53.94. Let's see if I can copy this. Oh, I can't. Okay. Negative 53.94.04. 53.94.04. 94.04. Let's get our snipper tool. So here's our graph. Copy and go back. All right, so paste. So the graph is looking something like this. I cut off the numbers there. Let's see. I don't know what happened to the spacing. It's kind of a bummer. Okay, so not the best graph ever, but here we have it. See if I can spread it out a bit. Okay, so remember the red is original, the blue is the derivative, okay? And then I think, so here we want to use, we graph the function, right? And so we want to figure out at time t, at time 2, right, what value did it have? So if you just kind of go over here to 2, $14.62.50. $14.62.50. So V at 2, value at 2 is $14,062.50. Okay? Quite a drop, right? Better to buy a used car. All right, so now we want to find the rates of change of the value with respect to time when t is 1 and t is 4. So, so our value, the change of the value with respect to time, we just did that on the calculator. So we'll just do v prime at 1. I believe that was negative 5394.03. Let's see. I'll check that. And then v prime at 4 is, going back, we have, so v prime at 1. $53.94. It's supposed to be 04, so I'll change that. And then at 4, this way, negative 2275.61, negative 2275.61, negative 2275.61. And this was supposed to be 04. Okay, so here we go. We already graphed v prime at t, right? And if you look over here, you can see, so remember v prime at t was this graph here, okay? And so what would you say the horizontal asymptote for that graph is, right? So the horizontal asymptote is just at v prime at t equal to 0, right? So basically what's happening here, right? We've got, actually, you know what, let's just call this y is 0. Y is 0. So this is the horizontal asymptote, for v prime at t. Okay, so let's check it out. So when we're looking at this graph, so let's go back to this one here because we can manipulate it. As you look at this graph here, right, at time 0, your car is worth 25,000, right, what you paid for it. Now, you're dropping exponentially, which means it's a rapid drop, and then it's going to start leveling off, right? So if you kind of look here and you go out to, you see here, year 9 years after you bought the car, right? Your rate of dropping is getting ever slower because there's only so much dropping that you can do before the car has no value, right? So it's going to get closer and closer and closer to the instantaneous rate of change of the value with respect to time is going to be 0 because you can't, go into a negative value, right? So as you can see, if we kind of bring in this graph, it's very, very rapid. Our domain starts at 0. It's very rapid at first, and then it's going to start leveling off, and after about 5 years, it starts leveling off a little bit more, really, once we get to year 8 or so, right? So let's go back. And actually, we've got a big space here. Let's get a better screen capture of this guy. we go. That's better. Okay, that's good enough. Okay, so we'll get a better screen capture of this now. Do a new one. Ready? Not sure why it went away. Okay. Okay, so we'll copy this guy. And come back here. Paste. Okay, so perfect. We've got our screen capture. So initially what happened, you know, so initially the value of the car drops very quickly or decreases very quickly, you know, after really it's after what, about 13 years or so. So it starts leveling out. Right. So all right, so that's it for this section. I'll make sure my regular graphing calculator is installed for the next one. Sorry about that. Again, had to get a new computer. I was having glitches, but it'll get better. All right, thanks. Bye.